In the first video, when we discussed the formulation of the principle of special relativity, we argued that, we said that Einstein accepted Maxwell laws as good laws of physics. We haven't studied these laws, but from one of them, or from the consequences of several of them, which are the constancy of the speed of light, c, in any inertial reference frame, we have found that the transformations that preserve these laws are the Poincaré transformations. And the discussion of the first day tells us that the rest of the laws of physics should also be invariant under Poincaré transformations and the full Poincaré group of transformations. At the same time, this implied that the Newton laws of motion cannot be good laws of physics. Okay, they had to be changed, reformulated, or whatever, in order to make them invariant under Poincaré transformations. So we are going to try to find a replacement for these Newton laws of motion, which is invariant under Poincaré transformations. What we are going to do here is a typical game that theoretical physicists play, which is to try to guess what the laws of physics are, just based on symmetry principles such as invariance under Poincaré transformations. This is never enough to find what are the true laws of physics. It just selects possibilities which agree with very general principles that we believe are true and that the laws of physics should satisfy. You find candidates. In general, you find a list of candidates that satisfy these symmetry principles, and then only by experimentation you can select those which really agree with experiment and with the natural world. However, we are not going to do experiments, but there is something that we can do, which is to impose an extra condition on the candidates to good laws of physics. So on top of satisfying, on top of the requirement that they should satisfy the symmetry principles, in principle, for instance, they should be Poincaré invariant under the Poincaré group of transformations, we are going to impose the condition that when the speeds that appear in the problem or in the law are smaller than much smaller than the speed of light, one should recover the standard Newton laws of motion. So we are going to demand Poincaré invariance. Plus the right non-relativistic limit. If we add to these conditions another condition which is always, sometimes it is manifestly expressed and some very often is not, such as simplicity, we are going to choose the simplest possibility that satisfies these conditions. In general, you have a very reduced list of candidates of laws of physics. In this case, in fact, it will be just one. We are going to arrive to the right generalization in just very few steps. Okay, so let us take the simplest or the first law of Newton, which is the law of inertia. The law of inertia can be written in this form. Okay, we're using Cartesian coordinates xi, and for trajectories of the particle, which are xi of t, and t is the universal Newtonian time. This equation, which is true, is assumed to be true when there are no external forces acting on the particle, is invariant under Galilean transformations. Galilean transformations, for instance, only shift the time by a constant, so the denominator of this never changes, and the kind of transformations that they do to xi are linear in time at most, so this really doesn't change. Okay, so we're going to try to find an analog of this expression, but now invariant under the Poincaré transformations, and with the requirement that it reduces to this expression when the velocities involved are much smaller than the speed of light. So in trying to guess what is the right replacement of this law of inertia, which is special relativistic, we make first some observations. The first observation that we make is that in this law of inertia only xi's appear, but clearly if this is going to be a special relativistic invariant, Poincaré invariant, this law should also involve x0, because we know that the Poincaré transformations mix the xi's and the x0s. So even if you don't have x0 at the beginning, after the transformation you will have it. So only if you have x0 and xi at the beginning, you will have maybe x prime 0 and x prime I at the end. Another observation is that, maybe we should start by defining velocities. So the standard velocities in Newtonian physics are just these, which we can rewrite like this. Just we rewrite it like this to make manifest the fact that even if xi transforms linearly under Lorentz transformation, which is okay, x0 also transforms. So the whole thing does not transform linearly under Lorentz transformations. So we cannot use this x0 here. What can we use? Okay, the formulation the study of world lines that we have made in the previous videos tells us that a good description of motion is the world line, and in particular if it is parameterized by this parameter s. We could use any parameter, but this parameter has the property that it is invariant under Poincaré transformations. Okay, this is the proper time. Then if you have the world line expressed in this way, it is natural to take the derivative of x mu with respect to s. This is a vector tangent to the world line. It is sometimes called it is a 4 vector, or it is called the 4 velocity. It is just the relativistic velocity. Okay, on the one hand, it transforms as you should expect, really as a vector. These are the kind of objects that we want because they have good transformation properties. And if this is a vector, after a Poincaré transformation, you will get another vector with just primes, because S is invariant. This is the property that the coordinate time does not have. So this would be the 4 velocity. Then, just by analogy, also this formula involves the mu equal to 0 component, which is good according to the observation A. So finally, if this is the velocity, this suggests that the acceleration should be the second derivative with respect to the proper time, and that in absence of external forces you would have this. Since the S is invariant, if x mu transforms linearly, this whole thing transforms linearly. So let me write it explicitly. You have x mu prime ds x squared, and this is a Lorentz transformation, sorry, a general Poincaré transformation. You will have just this. Okay, the space-time translation is constant, so you take the derivative with respect to s is 0. So if this is 0, then by homogeneity this is 0. So if the law of inertia is satisfied in a certain inertial frame 1, then it is satisfied in any other inertial reference frame 2 related by a Poincaré transformation. Okay, so this is the transformation in principle, a good candidate certainly for the law of inertia. We just have to check that for small speeds, for speeds much smaller than the speed of light, this law implies the Newtonian law of inertia. So finally, let's see if this expression has the right non-relativistic limit. So what happens at the small speeds? At the small speeds, the difference between the time measured by a comoving observer and the coordinate time is really small. So really S is approximately like the coordinate time. This is the time measured by a comoving observer, and this is the time, the coordinate time. This means that the velocity is approximately equal to this, and this is okay, if I write this as a column vector, this is more or less 1, and vi divided by c, where these vi's are the Newtonian velocities divided by dt. Now if we plug this into we take another derivative, so we take the derivative with respect to s of e mu. Again, this is the, the derivative of this with respect to x0, and if let me write this as a vector just to write all the components, this gives 0, and the derivative of vi with respect to x0 and with another c here. Okay, so this equal to 0. Okay, this is this law, this 2 1 over c squared dvi dt equal to 0. Okay, because this is 0 only if all the components are 0. This factor doesn't really matter, and this is the same, okay, as the square xi dt square equal to 0. So approximately, and because of the fact that in this limit for small speeds s is very close to x0, we can replace it. We find that this law, this relativistic law, implies the non-relativistic one here. Okay, we can take this as the right generalization or the right modification, which is Poincaré invariant. Let me just make an observation, which here is useless because we are still in special relativity. But let me just notice that although dx mu ds is a vector, a contravariant vector in the more rigorous or more general definition that we gave before of a vector, d square x mu ds square is not a vector. It does not transform contravariantly under arbitrary changes of coordinates, only under Poincaré transformations. You can say that it is not a general vector, it is a vector, a Lorentz vector if you want, because only Lorentz transformations play a role here. So when we face the problem of finding the generalization of these laws to arbitrary reference frames, we will have to take into account this problem. And really this problem will lead us very, very far, this observation. So it is an important one. Now that we have generalized or found the generalization of the law of inertia, we can generalize the second law. Okay, the second law is this one in Newtonian physics, and as you know, this is basically a definition of the force. So let me put it in a box first, and what should we do now? Okay, there must be, and this is something that you know, it can be proven, a generalization of the mass, which is an invariant parameter m. This is the invariant mass. This is the one that really matters, because it is the one that takes the same value in any reference frame. And okay, we can multiply by it, because we know that this gives us the right non-relativistic limit, this acceleration. And okay, whatever we have on the right hand side we call f mu. Clearly this gives us the right generalization for the components mu equal to I, so the spatial ones, but we are forced to introduce a new another component mu equal to 0. So this f0 is really a new feature of the relativistic second law of motion. Now, in order to put to work this formula, we need examples of relativistic forces, F mu. Finding these forces out of the top of our heads, I mean, we could invent something, but it is much more useful to find forces in the way that we are going to do it, by writing interactions between particles and fields, and then finding what are the forces induced by these interactions. We will do this by constructing Lagrangians and actions for the motion of particles and interaction with the fields. This we are going to do in the next video.